The final lesson for this unit, and I think by far the most interesting, is the one where we try to take these models, like when we ask ourselves, what type of situation does a sinusoidal model represent? And sinusoidal models are very good for any sort of behavior that repeats. So for example, if you were to record the amount of daylight that we get each day. So the sun came up at such and such a time and went down at such and such a time. So we had X number of hours of daylight today, and you were to track that for over a year, right? What you would find is that the amount of sunlight every year more or less is the same, right? Because every year is just a repetition of the year that was before it. And you'd get something like plus, what would it be, plus 6? No, sorry. You'd get something like this, where, this is, say, June. This is June, and this is, February, where you have a lot less hours of daylight, right? So, and this, of course, whatever it did in 2019, it would do again in 2020, and so on. So if we wanted to make this a little more accurate, we could say, let's say so January, it would start kind of low, right? So let's move it over by 3 months. Oh, sorry, move it the other way. Right? So like January, February, it's really low, the amount of sunlight. And again, let's say it's more like probably fluctuates by 4 plus or minus 12. That's too much. 3 plus or minus 12. So something like that. So you get like 9 hours of daylight in January. And then you get more and more and more daylight as you get to the month 6, which is June. And then you start to get less and less and less daylight until you're back to January, right? And then you would the next year would just be like that again. And so, like, this type of situation, you could also do this for temperature, right? Like the temperature in January versus the average temperature in June. Now that graph might not be perfectly periodic because over time the temperatures are going up, right, because of global warming. But the idea that something could repeat over and over again is useful when you're talking about a sinusoidal function. So one of the very common ones is this one, to track if something rotating on a wheel. What would your height above the ground do if you were on a wheel, right? So again, let's just quickly make a wheel. So let's just make this wheel. So, okay, it says a rung on a wheel with the radius is 25, is traveling at a constant speed. It makes a complete revolution in 60 seconds. The axle of the wheel is 30 centimeters above the ground. Okay, so let's talk about what each of those things represent. Okay, so it says sketch a graph of the height of the rung above the ground during 2 complete revolutions, beginning with the rung closest to the ground. Write a sinusoidal model that models this situation. All right. So first thing to understand is that the complete revolution in 60 seconds means t is 60, right? Because it takes 60 seconds to do a revolution. Now the axle of the wheel is equal to the axis of the function. And therefore, in our function, we have y equals 30 would be the axis, right? And the reason for that is because if you think of, let's just draw a wheel, okay? So let's draw a wheel. Let's say it's located at 0, 6. It has a radius of 5. So imagine you're on this Ferris wheel, and we'll set a timer. So we'll say 120 seconds, and the increment will be. Actually, it probably makes more sense to do 24 seconds. Increment will be 0.1, and let's make a point. Okay, so we'll put a point on here. So we'll say a equals 0, 1. Okay, so let's say that's where you boarded the wheel, and then we're going to rotate a around the point 0, 6. and we're going to rotate it, let's see, so 24 would be 2 complete revolutions, so 720 and 24 equivalent, so t times 24 over 720. Okay. Sorry, I must have done that wrong because that didn't go very far. 720 over 24, let's put it that way. Oh, because I didn't say degrees. That's the mistake I made. I was probably right the first time then. Oh no, maybe not. No, I was okay. All right, so here we go. So here's a rung on a wheel, and you can see after 6 seconds, it's at the top, and then after 12 seconds, it's back to where it started, and then another 6 seconds, it's back to the top, and another 6 seconds, it's back to where it started, right? So now what we're going to do is we're going to graph what this would look like. So we're going to make a new point, and we're going to say it has, as an x value, it will have t, which is the time that has passed. As a y value, it will have the height of where we are above the ground. Okay? Okay, so you can see our height. So let's put a trace on this. So our height starts to rise very rapidly, right? And then it slows down, and it comes to a stop, right at the top, because you're not getting any higher at that point. You're starting to come down, and then you would start to come down, and then you would come down really rapidly right around there, and then you'd start to slow down as you reach the bottom, right? And then you would go up, and you'd come down. Now, let's make a comparison between the graph that I drew and the circle that is the model, right? So first of all, the thing you should notice is that y equals 6, which is the center of the wheel, is also the center of my graph, right? So like half the time I'm higher than 6, half the time I'm lower than 6. In the same way that the axis of the graph, half the time of a cycle you're underneath the axis and half the time you're above. So this is why the axle of the wheel is the same thing as the axis of the function, and it says it's 30 centimeters above the ground. So, you know, again, if I was going to draw this one, I would draw it a bit differently, but in my case, I drew it as 6 above the ground. Now, the other thing that we should be able to see from here is that if the axle is at 6, then the radius of the wheel would have to be the amplitude, because from the middle of the wheel, the highest you could possibly go is straight up 1 radius, and the same thing would be here. The highest you could move off the axis is 1 radius, right? So the radius of the wheel equals the amplitude of the function. Now keep in mind, radius is always greater than 0, and a is always greater than 0. Amplitude is always greater than 0, so they're both going to be positive. Okay, so now with that in mind, let's draw this wheel that we're actually looking at. So let's make a note about what we know. We know that a is 25 because, we know that amplitude is 25, so what I should say is absolute value of a is 25. We know that the period, the k value is 360 over the t, which in our case would be 360 over 60, which would be 6. And then we have the axis of the wheel is 30. Okay, now what we don't know, of course, is we do not know which model, and we do not know which d. Now, as you learned last lesson, these two depend on one another. So it's up to you to choose which model you want, right? Let's draw what we have and then see how we could edit it. Okay, so let's just say I don't know what I'm doing. I'm just going to pick a positive sine model. So a will be 25, k will be 6, c will be 30, and let's do a positive sine model. Okay, so let's redraw this thing. Let's make the circle bigger. So it should be located at 0, 30 with a radius of 25 this time. So quite a bit bigger. The point is going to rotate not around 0.6 but around 0.30. Okay, the axis is not 6 but y equals 30. Okay, and then the point A is 0, 5, is 5 above the ground. And then we're going to rotate, so t, it's not 5t we want, but t times 6, because 6 was our value for k. Okay, so I'm going to need to extend this now to be more like, it's going to have to go up to 120 because the period's 60, and let's see if I did this right. So if you go 60 seconds, right, you're right back to where you started, which is what we wanted, right? We wanted a period of 60, so it takes 60 seconds to go all the way around, and then it takes another 60 to do another cycle. Now, if I just draw, so let's say I forget the part about the model. So I know that I'm going to pick sine, I know that x is 6, I know that it's degrees, it's plus 30, and then it's 25. Okay, now if I draw a sine model is not the best for this, right? Because a sine model begins on the axis on the way up. So if you choose a sine model, you would need to shift a quarter period to the right, because that's where you locate a minimum on the sine model. The minimum on the sine model would be a quarter of the period to your left, so you need to push it over in order to have it start at the right place. Of course, this is not really the best way to do this. The best way to do this is to say our model is supposed to start at a minimum. And the reason why is because it says, beginning with the rung closest to the ground. That tells us our model is supposed to start at a minimum. Well, look at your 4 models, right? Let's just review our 4 models for a second. So we have, I'm going to draw all 4 of them. Function cos x degrees from 0 to 360. Oh, okay, sorry. Just fooled me there. Okay, so there's a positive cos model, right? Okay, then we have a function. Let's draw a negative cos model. So negative cos x degrees from 0 to 360. There's a negative cos model. Then we have a sine model from 0 to 360 degrees. Then we have a negative sine model. Okay, now which one of these things it makes the most sense to draw for the model that we want? So let's review. Negative sine starts at the axis and heads down. That's not an appropriate model for what we're doing. Positive sine starts at the axis and heads up. Again, not what we were asked to draw. Positive cos starts at the max and heads down, so that's not what I want. So it leaves me with negative cos. Now, negative cos is very often the right model to draw. Okay, so let's just let's go back to this. So the negative cos model starts at its minimum, so we could choose negative cos as our model and ignore d. And that is probably what you want to do here. Again, it's not the only way to do it, right? You could use a positive sine and move it. You could use a negative sine and move it. You could use a positive cos and move it. But if you use a negative cos, you don't have to move it because it starts at the right place. So therefore, our model should be negative 25 cos 6x plus 30. And that, right, if I draw that, so let's draw that now. So negative 25 cos 6x plus 30. Okay, so we'll go back here. So negative 25 cos 6x, I have to do degrees on GeoGebra, plus 30. And you see that my model here is 100% right on as far as where the person is at what time. Right? At 30 seconds, they're at the top. Right? At 45 seconds, they're on the axis again, right? At another quarter period, they're on the axis. Then I do 15 seconds forward, and I find they're back at the minimum. They're back at 0. Okay? So as far as your model, what your model should look like when you go down here to draw, okay? You need to do 2 revolutions, which means, so let's write down some things about how to draw this correctly. So I'm going to just move this down here. Okay, to draw this correctly, we need to think of what we need. So, okay, if in doubt, count by 1/4 of the period or 1/8 of the period if you have a lot of space. So if we count by 1/4 period, we will be counting by 15, and we will need 8 boxes in order to complete 2 cycles. If we count by 1/8 of the period, we will be counting by 7.5, or realistically 15 per 2 boxes, and we will need 16 boxes in order to complete 2 cycles. I would say in this case, you're free to count by 1/8 of the period because you need 16 boxes, right? And you have 1, 2, 3, 4. 1, 2, 3, 4 is 8. 1, 2, 3, 4, and 1, 2, 3, 4 is 16. So that would be what I would recommend here. You should count by 1/8 of the period, and that would be 15 will be every 2 boxes. So let's see if we can I'll just help you sketch this with a new window. Okay, so let's go to your box now and sketch. So every 2 boxes, I want you to count 15. So on mine, what I'm going to do is I'm going to write a distance of 7.5, but I'm going to zoom it out in such a way that we only see the 15s. Okay, so this is exactly what yours should look like. I mean, your y, of course, isn't going to look like this. So let's think about your y as well. Okay, so for x's, it's going to be blank 15, blank 30, blank 45, blank 60. Okay, and then what you're going to do for a y-axis, right? So we have 1, 2, 3, 4, 5 to work with in the y. For y, we need to reach a maximum of 55 and a minimum of 5, right? Because, of course, if the wheel is 30 meters above the ground with a radius of 25, the highest it could get is 55. The lowest it could get is 5, which is right above the ground. So to count to 55, I mean, you could make each of these 12, and then it would get to 60. But let's say we make each of them 10, and then 55 will just be a bit above the graph. Okay, so we'll make the y distance 10 like we have on mine. Okay, so let's go back over here, and we'll make the y distance 10. All right, now what do you know about this graph? You know at the point 0, you're 5 meters above the ground. Okay, that's what you know. That's where you boarded the thing, right? You know that 60 seconds later you have to be back where you started, and 120 seconds later you have to be back where you started, because it's periodic and it takes 60 seconds for it to complete a revolution. So those 3 points are given right off the bat. Now the other thing you know is that halfway between the minimums must be a maximum because of the way these functions work. So therefore, at point 30, so we could, first of all, we could draw the line y equals 30, which would be like the halfway line, so you can draw that. At 30, which is a half a period away, we would be at our maximum, 30 and 55. Now, 60 seconds after that, we would have to be at the maximum again, so 90, 55 should also be drawn. Okay, so let's just go in here and show the value here instead of the... Okay, so your graph might look something like this. Now again, the only way you can get it wrong, well, sorry, there's 2 ways you can get it wrong from here. One is you can just draw jagged lines, so don't do that. 2 is you can forget to draw the axis points. So halfway between 2 minimums is a max. Halfway between a min and a max is the axis. So if it's the min at 0 and the max at 30, it must be the axis at 15, and it must go through 15, 30. Okay? So then if you just, again, we'll just change that to just show its value. Now, again, halfway between the max back down to the min, the same thing has to happen. So 45, 30 would be another point. Now, 60 seconds after this point would be 75, 30, which is there. And then 60 seconds after this point would be 105, 30, which is there. Okay, so again, we'll just quickly go back to the value. So you should be able to sketch those points, okay, using the method I just showed. Then what you do is you draw negative 25 cos 6x degrees plus 30, and it perfectly goes through everything we said it would. And that's how you graph this. Okay, start with what you know. I know he has to be at the bottom. 60 seconds later, he has to be at the bottom again. 60 seconds later, he got to be at the bottom again. Halfway between each min is a max, so halfway between 60 and 120 is 90. Halfway between 0 and 60 is 30. And then halfway between each min and max, it has to go through the axis. So you just draw all the points at the axis. Notice, if you count by a quarter period or an eighth of a period, then everything will line up nicely with a, like a value that you've labeled. So that's why I suggested you should count by every 2 boxes is a 15, and then you have a really easy task of just move over 2 boxes, draw the next one, move over 2 boxes, draw the next one, move over 2 boxes, and so on. Okay, so that's how you draw it. All right, let's try number 2. I think we answered everything it asked, right? It said write a sinusoidal model that does it. We did that, and we drew a graph. All right. A group of students is tracking a friend who is riding a Ferris wheel. They know that John reaches the maximum height of 11 meters at 10 seconds, and then reaches the minimum height of 1 meter at 55 seconds. Max and min heights are measured from the ground. Determine a sinusoidal function that matches his height above the ground, and then determine his height at 78 seconds. Okay, great question. So it's the same thing we just did, but sort of working at it from a different angle. So again, let's start with the concept of what we know on the graph. Okay, so the graph again, it has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 boxes, which is not great for us. We needed to get to 78, which is like a cycle and a half. So well, yeah, okay. This is I don't know that there's a way we can easily do this on the graph here without knowing more. But anyway, let's write what we know, and we'll just approach it the way I'll draw it as we go, and you can sort of do your drawing at the end. So it says they know John reaches a maximum height of 11 at 10 seconds. So let's go over here, and we'll draw 10 seconds has a height of 11. Okay, so we know that that's where he is at the max. All right. Now, we also know that he's at the minimum, which is 1 at 55 seconds. So 55, 1. So we know that that's the max and that's the min. Okay. The question is, where is he at 78? So x equals 78. So how high is he? So it's like min, max, and then he's on his way up. And where would he be when he crosses that line there, at 78 seconds? Okay, so that's what we want to know. So again, if we're just drawing it by hand, we might say it was something like, as a guess, we might say it's like, 6 or 7 meters. I think I drew this a bit too wide. Anyway, let's see if we can figure this out. I actually may have drawn this too narrow. Let's see if we can figure it out. It says maximum and minimum heights are measured from the ground. Determine sinusoidal function, and then okay. So how do we know enough stuff to answer this? So first of all, what I would suggest is let's write down a couple of things. The max is equal to 11. The min is equal to 1. Okay, immediately, as soon as you do that, you can remember that maximum plus minimum divided by 2, minimum divided by, divided by 2 is equal to the axis. Okay, so we can use that right off the bat. We can also use the idea that maximum minus minimum divided by 2 is equal to the amplitude. And again, the amplitude, to remind you, is absolute value of A. The axis is actually C. So you can take the axis as C. The amplitude, you can't take that it's positive. We don't know if it's positive. It depends what model we're going to choose. Now, so let's do these. So these are easy enough to do, right? So 11 plus 1 divided by 2 is 6, so y equals 6 would be our axis, and our amplitude would be 11 minus 1 divided by 2, which is 10 divided by 2, which is 5. Okay, so we know for sure that y equals 6 will be our axis, and we know that 5 will be our amplitude. So let's say we did 5 cos x degrees plus 6. Now, this is not bad. You can see what I've drawn. It has the correct maxes and mins, but they're not really in the right spot, right? Now they have the wrong period, and they don't really have the right phase shift. So let's see what we can work out here. So we're going to use some of our knowledge from the idea from the previous question. To move from a max to the next min, maximum, to move from a max to the next min, we have to move 1/2 of the period. Okay? And think about what the reasoning is there. Because if we moved a full period, we would be back to another maximum. And if you think about what we did in the last question, we used the fact that a minimum is exactly halfway between two maximums, right? So if we were to say x equals b, x equals x of b for a sec, and then we were to reflect a across that line, we would know where the next maximum is. And then we would say, okay, then the period must be whatever, right? Of course, we're not going to do it this way. We're going to do it an easier way than that. But I'm just trying to show you visually how that would work. Okay, so let's do something easy here. So from maximum to minimum takes 45 seconds? Because at 10 seconds he's at the max, and then 55 he's at the min. So from maximum to minimum takes 45 seconds. Therefore 1/2 t equals 45. So t must be 90. Okay, and what that tells us is that if we take another point that's 111, right? That must be back to the max, because it takes 45 seconds to get down to the min, and then another 45 seconds to get back to the max. Now let's correct my model, right? If t is 90, then remember k is 360 over t, so k is 4 in our case. So let's take my model and add a 4 right here. And you can see now this is a pretty good model. The only thing that's wrong with it is that it is not shifted in the right way. So again, what I would suggest here, what makes this question hard, by the way, is we do not know at what height we started watching this guy. Do you see how that's different than the previous question? In the previous question, they told us that the model has to start at a minimum. It says beginning with the rung closest to the ground. It told us where the model started. This question does not know, we do not know where he started, where John is at t equals 0. Therefore, our best course of action is to choose a positive cos model and let d equal the location of the nearest maximum. In our case, d would be 10, and the model is positive cos. So the final model that I think we should have here is 5 cos 4 bracket x minus 10, because that's where d goes, right? D is positive 10, but we want it to be minus 10 because it's inside the bracket, and then plus 6. So that will do everything we need it to do. It will have an amplitude of 5, it will have an axis at 6, it will have a period of 90, and it will have its maximum sort of 10 seconds after the beginning of the observation. Okay, so let's see what that would look like if we add a little x minus 10. Okay, and then you can see that when I've done that, okay, so now you've got this perfectly. It has a maximum at the right place. It has the minimum at the right place. We know where the next maximum is, and we can use the graph to sort of see that the point we're supposed to be looking for should be maybe just above the axis, right? Just slightly above the axis. We'll find it exactly, but just visually you can kind of see where we're looking for. So just to note, you could also choose a negative cos model here, right? What you would do there is you would move it over by 45 seconds instead of Oops, I guess actually hitting coast would be good, right? Sorry, 55 seconds, right? If you use a negative coast with a d of 55, that would also work, because negative coast starts at a minimum. And so if you want to start your model over here, or for that matter over here, that would also be fine. Any of these are fine, right? There's many ways that you can do this. What I suggest, in general, the best rule, the easiest thing to do is if your model matches up perfectly with one of our 4 models, right? So remember, like our 4 models are these ones. If it starts at a minimum, starts at a maximum, or starts at the axis, then I would pick the right model, because I don't need to worry about d if I pick the right model. If it doesn't, or I don't know where it starts, or I'm confused, or any other reason is interfering here, then I would just look for the nearest maximum, pick a positive coast model, and let that d be the value of the nearest max. I know there's a max at 10. It says it in the question. At 10 seconds, there's a max. So let that be d, and make my model positive coast, and then I know I'll get it right. Okay. So again, this one you can just pause the screen and you can draw it, and when you're done drawing it, you can just unpause. But we could sort of fill in the gaps here. I guess we could. What would be halfway between 10 and 55? Would be 32.5, and 6 would be a point, and then half a period later would be 32.5 plus 22.50. No, sorry, plus half a period. And 6, right? That would be another point that you could sketch. Now, it said we want to know where he is at 78 seconds, right? So you can see, he's going to be, if he's at the axis at 77.5, he's just going to be barely above that. So to find where he is, let's just write this down. So to find where he is at 78 seconds, just sub 78 into your function. So h of, sorry, I'm just going to delete this because it's not useful to me. So our function, remember, h of t is equal to 5 cos 4 t minus 10 plus 6. So all you would be doing here is you would just sub in h of 78 into that. So put a 78 there, subtract 10, you get 68, multiply it by 4, you get 240 plus another 48, you get 288. You take the cos of 288, which we know is a positive number because it's in quadrant 4, but it's not a very big number, and then you multiply it by 5 and add 6. So you're going to get something just above 6, right? So we go h of 78, and we get 6.17 equals 6.17 meters above the ground. Okay, and that would be that's all you got to do. So this once you have the model, then of course determining his height is really easy. You just plug in the number and get it. Okay. I think this one, I honestly, I don't think you'll have any trouble with this. This would be a good check-in. If you can't do this, then I would rewatch what I did in number 1, because the radius tells you the amplitude, the revolution tells you the period, the bottom of the wheel tells you the minimum. So you kind of use the radius and the minimum to get the axis, right? So just think about this. The min equals 5, the radius equals 15, so the axis has to be 20, because 20 is a halfway point. If I go down 15 from 20, I would get the minimum, which is 5, which, and you can kind of go from there. It says sketch one cycle that represents the height of the passenger, starting with when the passenger gets onto its lowest point. So you use a negative coast model with d equals 0, right? So that's pretty simple, and then you just write it and draw it, right? So I think you can do that based on what we know. What I want to focus on, though, is this fourth question, because this will. There's actually 2 more. Okay, so let me just read this one quickly. The height of a tide given at a certain time of day is t hours after midnight. Is modeled using this function. Find the maximum and minimum. When is high tide? When is low tide? What is the depth of the water at 10 a.m.? Okay, well, let's just go through this one. This won't be too hard. Okay, so let's write it down. So h of t equals 4.5 sine 30 t minus 4 plus 6. And h represents the height of the tide, and the tide, and t represents hours since midnight. Okay, so it says A, find the maximum and minimum values of the depth h of water. Okay, so this is like us just working a bit backwards. Looking at the equation, I can see A is 4.5. I can see K is 30. I can see D is 4. And C is 6. What does this help me establish? I'm sorry, 4.5, not 45. Okay, what does this help me establish? I know that the maximum is C plus A, really plus absolute value of A, but since A is a positive here, it's okay. So C plus A is 10.5. The highest this tide could ever get is 10.5. Think about this. 6 is the halfway point, 4.5 is the amplitude. So you could move one amplitude up from that halfway point. The minimum would be, C minus absolute value of A, which in our case would be 6 minus 4.5 would be 1.5 would be the minimum. So find the maximum and minimum values of h of the water. So there we go. The highest this function will get to is 10.5. The lowest is 1.5. Let's sketch it quickly so you can see what I mean. So it's 4.5 sine 30 x minus 4 degrees plus 6. Okay. Now, if I draw the line y equals 1.5, you see the minimum. Y equals 10.5, you see the maximum. Y equals 6, you see the axis. Okay? So I've got the min, I've got the max, I've got the axis. Okay, what time is high tide? What time is low tide? Now that's a more interesting question. There's two ways you could go about this. You could try to solve it mathematically, which I think is what we're going to have to do. Yeah, I'm going to add it to that question, but let's solve it mathematically because that's the skill we should practice. You don't have to do it this way. You could reason this out. You could find the period. Sorry. Let's just do it this way quickly. So, okay, so the period, right? The period we know is 360 over k, which in our case is 360 over 30, which is 12. That makes sense for a tides question because it takes 12 hours for the tide to repeat, right? So 12 hours. So 12 hours is the period. Now consider our model. We are using a positive sine model shifted 4 hours to the right. Okay? So in other words, at t equals 4, the height would be 6 and on its way up. Okay, so let's draw a quick table for this. Actually, you know what? I want to draw a third. So let's insert columns to the right. So let's say let's look at sine a different way. Sorry, yeah, I see what I want to do here. So let's look at sine a different way for a minute. Let's say time and sine. Okay, so sine we know was 0 and then it was 90. But instead of 90, I want you to think of 90 as a quarter period, and then a half period, and then 3/4 period, and then a full period, right? And what does sine do? It's at the axis, then it's at the max, then it's at the axis, then it's at the min, and then it's at the axis again. And it's completed one full revolution in one period, right? Now, you're used to seeing this like 0, 90, 180, 270, 360, but those numbers, you could think about them as fractions of the period instead, right? Oops. Okay, so this graph counts up by 1/4 of the period, which is what all sine graphs, what all sine graphs we've ever drawn. Now, let's start with our idea here. Now, in our situation, okay, the time and then the sine, the value of sine. What's sine doing? Okay, Now ours doesn't start at 0. It starts at 4 because it was shifted over 4, right? And we know that the period is a quarter t. So in our case, 1 quarter t is equal to 1 quarter of 12, which is 3. So if I go to the next point would be 4 plus 3, which is 7. The next point would be 7 plus 3, which is 10. The next point would be 10 plus 3, which is 13. The next point would be 13 plus 3, which is 16. Now notice, between 4 and 16 is 12 hours, right? Because the period is 12 hours. So we moved up by a quarter of the period each time, and we got to where we wanted to go. Sorry, I'm just going to try to give myself a bit more room here. Okay, now what is sine doing? Axis, max, axis, min, axis. Now what's the answer to the question? What time is high tide? What time is low tide? Well, high tide is at 7. Low tide is at 13. Now what is 13? 13, it's 13 hours after midnight, right? So let's write it down. So high tide is 7 hours after midnight. So 7 a.m. Low tide is 13 hours after midnight, otherwise known as 1 p.m., right? You could just say 13 hours after midnight would be fine. Okay, and that's how you could do this without really doing any solving, because you can just reason about the way sine works. If you get this idea that every point is a quarter of the period moved over, then you can just move your sine over and just write this, and you know where the maxes and mins are. Let's say we didn't know how to do that. And let's say instead we wanted to take our h of t function and set it equal to the maximum. So let's say find the max. So let's just say method 2. Method 2, find the maximum by solving. So h of t is 4.5 sine 30 x minus 4, or t minus 4, plus 6. Okay, and we know that the maximum is 11, what was it, 10.5, I think? That's what I said the max was? 10.5. So let's set our function equal to 10.5 and see what we get. 10.5 equals 4.5 sine 30 t minus 4 plus 6. So how would you solve this? You would take the 6 to the other side. 10.5 minus 6 equals 4.5 sine 30 t minus 4. Okay. Then you would, so you'd have 4.5 equals 4.5 sine 30 t minus 4. Okay. Divide both sides by 4.5. You'd have 1 equals sine 30 t minus 4. Now, in order to get rid of sine, you need to inverse sine, right? So what happens? Oh, sorry, no, I need an actual -1 up there. It's not inverse sine. So what happens when you inverse sine both sides? So we're going to go inverse sine. Oops. 1 equals inverse sine. Of course, you don't have to write this, but I just want to show you what I'm doing. Okay, so we take the inverse sine of both sides. Now, when you inverse sine 1, you're going to get 90. And you can't consider two answers for this, because if beta was 90, then your quadrant 1 answer would be 90, and your quadrant 2 answer would be 180 minus 90, which is also just still 90. So 90 equals beta, but is also unique in that it is both, Q1, you have theta equals beta, and therefore, in our case, theta equals 90 degrees. But in Q2, right, you have, theta is equal to 180 minus beta, which in this case is also 90 degrees. So there really only is one answer here. It has to be 90. Okay, so watch what happens now when this is 90. So the left side, inverse sine of 1 is 90. The right side, inverse sine and sine cancel out, and you get 30 times t minus 4. Now solve this. Divide both sides by 30. you get 3 equals t minus 4, and therefore t is equal to 7, which is the same answer we got above, right? I said it happened at 7 hours after midnight. So therefore, the high tide is 7 hours after midnight. Now again, the same thing would happen if I wanted to look for low tide. Let's just quickly do the low tide solution so you can see it. Low tide. Okay, so low tide was 1.5 equals our equation. So we take our equation and set it equal to 1.5 this time instead of 10.5. And again, we'll bring the 6 over. We get negative 4.5 equals 4.5 sine 30 t minus 4. And then we divide both sides by 4.5. We get negative 1 equals sine 30 t minus 4. And then we inverse sine both sides. Now, when you inverse sine negative 1, your calculator is going to say negative 90. Okay, now we don't want negative 90 because that would be, we don't want a negative angle. So we have to think, what does negative 90 mean? So let's just write inverse sine. Inverse sine of negative 1 would be equal to 30 t minus 4, right? You take the inverse sine to get rid of sine. Now, inverse sine of negative 1 tells you beta is equal to negative 90 degrees. Of course, we don't want negative 90 degrees because that would be like before midnight. A negative angle is before midnight in our example. So let's make it positive. How do you make negative 90 a positive angle? Theta, right, would have to equal 270 degrees. So 90 rotating in a negative direction is the same as 270 rotating in a positive direction. So we say theta is 270. So 270 equals 30 t minus 4. So divide both sides by 30. You get 9 equals t minus 4. And therefore 13 equals t. So therefore, 13 hours after midnight is low tide. Midnight is low tide, and that is 1 p.m. That's 13 hours after midnight. Okay? So really, really nice question. It takes a lot to understand this, right? It leans on what you learned last unit as well. Let's do one more. And then I'm going to ask a different question here. So let's do this, and then let's do part B. When is the water 8 meters? When is the water 8 meters deep? Okay, so let's just do a challenging question so you have it for next year, really, because this stuff is important next year if you're taking advanced functions. So let's do this one. So the depth of the water at the end of a pier is 2 meters at low tide. So our minimum equals 2. Our maximum equals 12. There are 6 hours between low tide and high tide. So minimum to maximum is equal to 6 hours. And we know that that's half a period. So we know that 12 is equal to a full period. Again, it's a tides question, so 12 is always going to be the period. But that's how you could reason it out. It says the first high tide occurs 6 hours after midnight. So I'm going to use that information to construct the rest of my model. So let's highlight it in green and how about red? Okay. What I'm going to use that piece of information to show is that a positive coast model would need d equals 6 because high tide is a maximum, right? High tide is a maximum. Let's just put some text down there. And positive coast starts at a high tide. So let's write down what we know. The min and max is 2 and 12. So A would be 12 minus 2 divided by 2, which is 5. And C would be 12 plus 2 divided by 2, which is 14, divided by 2, which is 7. We also know that K is equal to 30 because K is 360 divided by T. So what do we have here? I said a positive cos model, so 5 cos 30 x minus 6 plus 7. Okay, and that would cover everything we need. Let's quickly draw to prove it. So 5 cos 30 x minus 6 plus, sorry, I need degrees, plus 6 was the, or plus 7, I think, in this question, right? Okay. Now, how does this show what we were just working on? It says 6 hours after midnight, we should be at a maximum. So where are we at 6 and f of 6? We're at a maximum. 6 hours after that, we should be at a minimum. And 6 hours after that, so 18 and f of 18, we should be back to a maximum. Okay? So that's how you could see. You could see a negative cos model would also have worked here very nicely. But anyway, it doesn't matter. This model will work fine. Okay? So write a sinusoidal equation that represents the depth of the water. Okay, we've done that. We used a positive cos. We found out this from the period. We found out this from the min and max, this from the min and max, and we chose a positive cos because we knew where we knew where a maximum was, and that's easy. Now, when is the water 8 meter deep? Now, if I draw the line y equals 8, and again, let's clarify my question within the first 24 hours after midnight. Let's not do 24 hours. Let's do 12. Well, no, even this this isn't going to be so good. Within the first 24 hours after midnight. Let's do the 24 hours. Okay, so when is the water 8 meter deep within the first 24 hours after midnight? Because, of course, every day would be the same, right? It would be the same thing over and over again. So let's try and do this using what we did last time. So 8 equals 5 cos 30 x minus 6 plus 7. Okay, so basically, so this is now I'm looking at part B. Okay, when is the water 8 meter deep? So I take the equation and I divide and I set it equal to 8. Now I solve it the same way we were solving it a minute ago. So I bring the 7 over. 1 equals 5 cos 30 x minus 6. 1 over 5 equals cos 30 x minus 6. Okay, and now I have to inverse cos 1 over 5. And this would be equal to 30x minus 6. Now, in the previous question, we got lucky because we were looking at an example where it was equal to 1 or negative 1, and there was only one case here. So let's do case 1, quadrant 1. Where's the other place that cosine is positive? Quadrant 4. In quadrant 4, theta is equal to 360 minus beta. In quadrant 1, theta is just equal to beta. So whatever our calculator tells us is going to be one answer. So let's inverse cos 1 over 5. So in this case, we go inverse cos 1 over 5, and that gives us what? So inverse cos 1 over 5 gives me 78.46 degrees. Okay, now in quadrant 1, we can just say theta equals 78.46 degrees, and we can just keep doing the question. So 78.46 equals 30 bracket x minus 6, and then we get, divide them by 30, so 78.46, oops, 78.46 divided by 30. Wait, what is it doing? 78.46 divided by 30. Is equal to x minus 6. And therefore, let's just do 78.46 divided by 30, and then a plus 6 would be 8.62. Okay, so we have one answer here. It would be 8.62 hours after midnight. Let's test it. 8, so B, which is 8.62, and then f of B. And you notice that at that point, it's exactly 8 meters above the sea level, or above, like 8 meters deep, which is what we wanted, right? At that time exactly. Now, what's the other time? Here, inverse cos of 1/5 still gives me 78.46, but I know that my calculator can only tell me the beta. It can't tell me that there are two answers that I'm looking for. In this case, I know theta would be 360 minus 78.46. So theta, let's just quickly do that. 360 minus 78.46 is 281.54. Okay, and 281.54 equals 30 bracket x minus 6, and therefore 281 divided by 30 plus 6 equals x. And let's just do 281.54. Okay, and what you find here is that x equals, well, let's find out. So c divided by 30, and then d plus 6 is 15.38 after midnight. Okay, so let's try that one. So e and f of e gives me another point where it's exactly that time. Now, the final thing about this, the final thing to understand, so when you give an answer, consider whether, okay, remember that a periodic function has the property, so take us right back to lesson 1, f of a equals f of a plus t. Therefore, it must also have a height of 8, one period before and after each of our answers. So we have to ask, can we add or subtract 12 from either of our answers and still stay within the first 24 hours as the question indicates? Because think about it. If I draw this function, function f, between 0 and 24, you've given me the two answers, but you can see they're not the only two answers. There are two other times when the tide would be at 8 meters, right? One of them would be 12 hours before E, and one of them would be 12 hours after D. So let's show how we could do this. So consider answer number 1. Take answer number 1. Number 1. So t is equal to 8.62. So t plus a period, so 8.62. So for 8.62 minus a period would be negative, right? Because you got 8.62 minus 12. And that's going to be like negative 3 or something. So we can ignore that one. But 8.62 plus 12 is equal to 20.62, and that is in the first 24 hours. So I suspect there's another answer here at 20.62. Let's draw it. 20.62 and f of 20.62, right? And there you go. I found the other time that the height is exactly 8. Of course, it's off by a bit because it's rounded, but you get the idea. Take answer number 2. T in this case was 15.38. Now, obviously, if we do 15.38 plus a period, we're going to be bigger than 24 because 15.38 plus 12 is equal to 27.38, and that's bigger than 24, and therefore we can ignore it as it is outside the first 24 hours. On the other hand, 15.38 minus t, right, is equal to 3.38, and that is in the first 24 hours. So 3.38 is kept since it is in the first 24 hours. Okay, so 3.38 and f of 3.38, and there you go. I've got the fourth answer. Now again, this is a little much for what we need to learn today, but I want you to write, it might be a good thing to put, in your notes or on your CPT if you're doing this in 2020, because it will help you in the future, right? And just it'll give you a baseline to sort of come back to next year as like, yeah, okay, I've seen this before. I'm not starting from 0, right? Anyway, so that's good. Please, any questions? There's some extra practice here. And here's a good question here. What time was it when the tide reaches 4 meters? Really, really good question, right? Try that one. If you can do that one, then you know how to do this. The assignment questions will also really help you with this stuff, okay? So please, any questions, just post to the site.